Okay, we're solving for t. What's the first step to get out of this logarithmic form?
You switch it to 64 with the exponent of t
64 to the power of t
equals 2.
equals 2. That's the definition of a log. How can I rewrite 64? 2 to the 6 raised to the power of t is equal to 2. What do you do on the left? What does that become?
T squared.
Not t squared.
16.
16. We multiply those powers. Is equal to 2 to the first. What's a logical conclusion to make here? 6t is equal to 1, so t is 1/6. Okay, when you're eating, you don't breathe at the same time. The food goes down the wrong pipe, as it were. I'm ecstatic with that finally. I found out what t is. Right. This one is solved for t. T is already there. It's not like, great, oh, so that's what you were talking about too. This is not the same as when we make it equal to z. Like if the directions were simplified, very different. This one is solved. And this morning we were talking about that as well. What do the directions say? This one's solved.
How can we put a 1 over the 2?
How come well, we don't normally do that. 2 to what power is this?
Okay, 1.
So I just wrote it here so it would be easy for you to see that 1 was equal to 6t.
Okay.
You don't have to do that, but you have to get 1 equals 6t.
Okay.
Okay? Anybody else on this? The bulletin didn't go through. We don't have a bulletin. This is for you. Yeah. This is just for you. I thought you'd appreciate that.
Yeah, great. Was that a series or?
That was a scene. The scene was very slow.
That was great. Thank you for that.
Yeah,
Great way to start my Thursday.
it's all right. Least I could do. All right, we're going to take a look at a couple of simple functions here. And this is just continued. Yesterday we did the first half.
Yeah.
Now we're continuing on with the notes of subject. So this is the same. This is what we did yesterday.
Yeah.
These are the same notes. I'm just going to continue them, and I'm going to save these as day 2, just because this will have day 2 information. So we're starting off with an inverse. The process for finding the inverse, you guys are already really pretty good at. The downside on finding the inverse with these is that you need to remember to use the definition of a log. All right? So what is the process telling us to do when we, for example, want to say find the inverse for A? How do we do it? What's the process telling us? Switch the x and y. So this is going to become x equals 8 to the power of y. And then, no, not what do you do here. Switch the x and y, and then solve for y. The only way we're going to solve, you can't y root both sides. What are we going to do? Use the definition of a log. We're going to press the button. So this is going to become log base 8 of x equals y. And then probably like to see it written log base 8 of x. That's the inverse. Y equals 8 to the x. The inverse is y equals log base 8 of x. Now this one's already in logarithmic form. We want to switch it to exponential form ultimately, but we're looking for the inverse. So what should the next line say?
X equals actual log, or the actual log of x minus 4, or y minus 4.
X is equal to the natural log of y minus 4. You switch the x and y's, and then we, bless you, to do what?
Solve.
For
Y.
y.
Gotcha.
So simple, switch x and y. Solve for y. You don't have to be so impatient.
Hmm?
Relax.
No, I was just saying it.
Okay. You seem
Going
like
the
you're a
long
little
way.
uptight about it.
No.
All right, so how are we going to solve for y? We're going to use the definition of a log. What is that going to become? Definition of a log, right here. What do we write? Make the loop. If it helps, we can write it like this. Natural log of y minus 4 is equal to x. Make the loop. Go ahead.
So y minus 4.
No. I want you to start with something else.
So e to the x. Yeah, equals y minus 4.
You were probably going to say the same thing, right? But
Yeah.
I want it, if you're making the loop, it's base to this power equals what you were taking the log of. If you don't know the definition of a log to do that, and you didn't study it well enough to do that, you are behind today. And you have to understand, you made a choice, you're behind, what are you going to do to fix it? Now, how do I solve for y? Add 4. Don't add it to the x. It's e to the x plus 4 is equal to y, or y equals e to the x plus 4. Make sure that x is the power and the plus 4 is after. This is 0, 4 translation vector on that parent graph. What does ln mean? Yes. What does that mean? What does the natural log mean? It means log base e. In your notes yesterday, you should see that when it's log base e, we don't write log base e, we write ln of x. Log base e of x becomes ln, or natural log of x. We do not write log base e ever.
But we still have to.
Everybody follow those two? How do you find the inverse? You switch x and y, solve for y. The way you solve for y is to use the definition of a log. Okay, so we can do this one. It's a little more complicated. X is equal to 7 to the power of 2y. X is equal to 7 to the power of 2y. How does that change when we use the definition of a log?
Log base 7 of x equals 2.
Log base 7 of x equals 2y. We have 2 people, 3 people who are doing this. The rest of you either don't know the definition of a log, or you're being shy today for some reason. I'm concerned that you really aren't clear on the definition of a log. No questions from homework. 0. No questions on what we're doing here. 0 so far. And no input on what we're doing, except for 3 people. Is anyone not seeing how we're going from this line, the first line, to the second, and the second to the third? Okay? The definition of a log, roughly, is log base b of x equals y, if and only if b to the power of y equals x. You need to be able to switch back and forth based on what you have and switch to the other form whenever necessary. This red line right here, do you understand how I got this? This is in this form or this form? Exponential or logarithmic? The exponential. What is in the position of b? 7. What's in the position of y? 2y. And what's in the position of x? X. So a lot of coincidence with letters there. Where the letter b is, you're going to put 7. Where the letter x is for this problem, you're going to put x. And where the letter y is, you're going to put 2y. That's the definition of a log. It's literally putting the round peg in the round hole, etc. So we've used the definition of a log. How do I get rid of the 2? You could divide each side by 2, but that's going to be really confusing looking to us. Log base 7 of x all over 2. What's another way that we could do it? Multiply by a half. So you would get 1/2 log base 7 of x is equal to y. And then you typically turn it around and write y equals 1/2 log base 7 of x.
Why would you want to divide it by 2?
Well, if you write log base 7 of x, and you put it all over 2, what is that over 2 doing for you? But it's not. It's divided by 2. And what does that mean for us? It doesn't mean anything to us. What does this 1/2 mean to you? What does this mean to somebody else? What is this 1/2 telling you? If you're not looking up here and paying attention right now, you should be. We're looking at this line right here. What does the 1/2 tell you about this equation? It has a vertical stretch factor of 1/2. This tells you nothing. This is misleading to us in what we've learned. We've learned about translation vectors, vertical stretches, and horizontals. We don't have one where we take function and put it all over 2, for example. Mathematically, it's correct. It's just not where we want to go in terms of how we write our answers.
So the 1/2 would be like a in another equation.
Well, in this equation, the parent graph is y equals log base 7 of x. The vertical stretch factor is 1/2. The translation vector is 0, 0, and there's no horizontal stretching. We'll get to that in a moment. Let's see if we can do the inverse for D. All right, so what do we start with on this? How do we start this process? Switch the x's and y's. So x is equal to the natural log of y plus x. And now we need to solve for y. All right? So how can we use the definition of a log on this one? You're raising a fluff and you do.
You can switch it to e to the power of x
Is equal to
y plus 6.
y plus 6. So we're making the loop right here. E to the power of x is equal to y plus 6. That's the definition of a log. Sure. Okay, so e to the x minus 6 is equal to y. You can't put the y on the left on that line. Y ends up on the right when you subtract 6. Then we switch to e to the x minus 6. This line has to be here before you switch them around. Attention to detail.
Would minus 6 be equal to the translation vector?
It is. The translation vector is 0, negative 6. Parent graph, e to the x in that one. Okay. Everybody seeing those? So when we look at our parent graphs, 10 to the x, log x, or b to the x, and log base b of x, we're going to get what we call inverse functions. Okay? We can start with 10 to the x. This is a parent graph. The parent graph, y equals 10 to the x. Translation vector 0, 0. No stretching, no moving. What's the first thing you put on your paper? Horizontal asymptote through y equals 0, through the origin. Tell me a point on the graph. Right 1, up 10. 2, 4, 6, 8, 10. Another one.
Right, 0, up,
Up 1. And
left 1,
left 1, up 1 over 10. So we have 3 points. We're going to come across the asymptote, hit that first point and start heading up. And it's very steep when it's 10 to the x. Okay? Now take a look at this. We've just been looking at how we find inverses. Y equals 10 to the x. That's the function we just worked with. If we switch the x's and y's, we get x equals 10 to the y. And if we solve for y, you get log base 10 of x is equal to y. That means that y equals 10 to the x and y equals log base 10 of x are inverse functions. Those are inverse functions. So if that's true, if log of x, common log of x, and 10 to the x are inverse functions, then they should reflect in the line y equals x. So we should have a reflection in the line y equals x, which means that the point 110 reflected in y equals x should become the point
-1.
How do you find the inverse? So if the point is 110, the inverse would be 10, 1. Right here. Look at where this guy's looking. He's looking at the mirror. He's going to see his reflection right over here at 10, 1. We have a point 0, 1. Looking in the mirror, its reflection is going to be at 1, 0. And we have the point -1, 110. It looks in the mirror and it sees its reflection at
-1.
1 over 10, -1. You have a horizontal asymptote for y equals 10 to the x. The equation of this asymptote is y equals what? This green asymptote. 0. Y equals 0. In the inverse, what will that become? X equals 0. So you will get a vertical asymptote for a log function. Come on. So your horizontal asymptote of y equals 0 will become a vertical asymptote of x equals 0. when you graph these, you're going to climb the wall. The vertical asymptote is going to act as a wall. We're going to come up along the wall, hit our points, come over the top. And that was not as slow as I would like it to be. Bless you. A bit better. It's going to look more or less like that. You can see that this blue graph is reflected through the yellow, and you get the red graph. Exponentials and logarithmic functions are inverses. Exponentials and logarithmic functions are inverses. This is common log of x, which means base 10. This is exponential, base 10.
Is the line of reflection always going to be y equals?
For inverses, yes. And I don't need you to graph that. I'm just doing it today for just so you can see. But the reflection for inverses is always y equals x. There are other reflection lines, but when we talk about inverses, they reflect through y equals x.
It's still y equals x because of the translation vector.
No, these are parent graphs.
Oh.
If you have a translation vector and you find the inverse of that, yes, it's still going to have the same y equals x mirror. Okay. Everybody good so far? In y equals 10 to the x, what's the domain? All reals. All exponentials domain are all reals. What is the range? Y is greater than 0. So if we switch those, what's the domain for the log function? Y equals common log of x. X is greater than 0. All you do is switch x and y. So now y is greater than 0 becomes x is greater than 0. And the range for a log function becomes all reals. So the way I've put it on here is I used interval notation. You can use Sepulveda notation. I don't care which one you use. For 10 to the x, the domain is all reals. That's interval notation. The range starts at 0 and goes up. The horizontal asymptote is y equals 0. When we find the inverse, the common log of x, this domain becomes the inverse's range, all reals. And this range, 0 on up to infinity, becomes the domain of the log function, greater than 0. The horizontal asymptote y equals 0 becomes the vertical asymptote x equals 0. And that's true for every exponential and logarithmic function, regardless of the base. This is true for every exponential and logarithmic function, regardless of whether it's 10 to the x, 8 to the x, 3 to the x, or log base 2 of x, log base 20 of x, log base 5 of x, doesn't matter. None of those things will matter. Everybody good on the domain and range? Horizontal and vertical asymptotes? So the parent graph for a log base b of x, this is the movements that we have. And they are the reverse of 10 to the x, or b to the x. Remember when we had b to the x, we went right 1, up b. Now we're going to go right b, up 1. In an exponential function, we went right 0, up 1. We're going to go right 1, up 0. And in the b to the x function, we went left 1, which was a negative 1. And we went up 1 over b. So we're going to go right 1 over b, but down 1. Your vertical asymptote will always be x equals c. Will always be x equals c. Yes,
Where is C of this?
you should know where C is. It's the same place it's been since chapter 2. Where does C appear?
Next to X.
Next to X, and you have to be,
The opposite.
well, but what operation mathematically has to be?
Oh,
Adding or subtracting, not the multiplying. That's B. So if we had a C in this, you'd have X minus C up here, or X plus C type of thing. And then you take the opposite. But again, we don't have that here, so C is 0, right?
Yep.
So in all the parent graphs, C is 0. Everybody good here? So when we look at an example, this is a parent graph, but the parent graph for this is base 2, log base 2 of X. No translating, no stretching, just graphing the log function. All right? And I'm going to show you two things now. The basic graph with our 3 points, and then because we're using base 2, and you might feel a little constrained, how could I find another point to graph just to make my graph look better? So we start at the origin. What's the first thing I do for my, we don't even have a translation, so what do we do when we find where we're starting? Vertical asymptote right away. So this one, we put a vertical asymptote for the origin. Now if you look at the previous slide, your notes that you just took, most of you wrote it down, from the origin. If we're going to graph from the origin, give me one of the 3 points. You don't have to be the first one, whichever one you want. Give me left, right, up, down.
Right.
Did you just write it down? So you did write it down. Jennifer, what did you write down? So how do I get to my first point?
Right.
Okay, so in this case, what are we going to do? Right 1/2, down 1. Sort of taking notes is a pregnancy question. Either it's a yes or a no. You're either taking notes or you're not, and sort of is probably more than not. Crystal, give me another one. Right 1, up 0. Always goes through right 1, up 0. Jennifer, give me another one.
Right. Yep. 1.
And what's B for this one? You sure?
Yep.
You are? You're sure that the base is 2? Okay. So right 2, up how many?
1.
1. So you can see climbing the wall is easy. We're going to come up here along the wall, hit, boom, and we're going to roll over the top. But you might not know where to go from there. It's hard to judge. So finding the, go ahead. Are you sure? How I got right 2 up 1. What do you have in your notes? What do you have in your notes? Say it again. Right B up 1. What's the base on this function? Y equals log base B of X. That's what we just did right here, right? So in this graph, what's the base? So it's right B, which is 2, up 1. Okay? Now, this is where understanding a log is going to help you a lot. Because some of your graphs are going to go up here too quickly, and that's going to be a problem. So how does this work? 2 is raised to the power of y. So what have we done for y? We've done -1, we've done 0, we've done 1. Let's do y is 2. 2 raised to the power of 2. What would x have to be? 4. So that means right 4 up 2. If y was 3, How many right do I go to go up 3? 8. 2 to the power of 3 will give you a right 8. And that gives you a much better impression of how this graph is going to look. So you're putting in a value for y, for example, 3. The definition of a log says 2 to the y. Correct. So we're going backwards on it from what we would typically do. But it works, and it keeps us with integer, 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 which is even better. Questions on this graph? If you don't understand the definition of a log, this is going to be a train wreck. It's not pretty. Now this is a fractional base. Okay, again, our software has not been updated still, but this is a fractional base. It's a parent graph with no stretching. But it's going to look a little bit different. So you've got to stick to what Jennifer, and Christo said with the basic rules right here. Right 1 over b, down 1. Right 1, up 0. Right b, up 1. B is the base. So when we look at this problem, what is the base? 1/3. So we have no translating, so the first thing we put on our graph is before that. Before that. Vertical asymptote. Then we go right 1 up 0. That's always the easiest one to do. Right 1 up 0. 0, how about another one? You got 2 to choose from. 0, 1 is not a choice. I have that one. You have 2 other choices now. Why write 3? What does it tell you to do in your notes, right? I'm having a hard time hearing you. Okay, what's B? Right, 1/3, but which way do we go? Right, 1 over B, right, 1 over 1/3, and then which way do we go from there? Down 1. What's 1 divided by 1/3? 3. So right 3. Is that what it says? Right 3, down 1. Perfect. Anna, last one. Sorry, I got you with a mouthful.
1/3 up 1.
Right 1/3, right B, up 1. Because our base is smaller than 1, it causes our graph to flip over. Just like it did when we had a base smaller than 1 on the exponentials, it caused it to flip horizontally. This one is caused to flip vertically. So you're going to kind of come down the wall here and hit your points. Should look like that.
Why do we have to find more points for the last one?
You don't. It just, even on this one, I might want to find one more just to see how much am I going to go over. On the last one, what happens without these points? They're going to go this way, which means I think you're off significantly. If you're coming over, you got to make sure you come over enough. I'm not going to mark you down for not doing those points. Kids who are going to honors need to realize this is what you're expected to do. You're in Algebra 2. This isn't Algebra 1. Algebra 1, I'd be happy if you got 2 of the 3 points. Okay? In Algebra 2, I want the correct graph, not a half-ass graph. We want to see this is really what it looks like. So I come up here, I hit this, I hit this, I hit this, and I'm not sure how much of an angle do I need to roll. Find another point. It's really easy to do. Even with a fractional exponent, we can do a fractional exponent of -2. So 1/3 to the -2 power is 9. So I have to go right 9 down 2, and you can see my graph is way too coming down that way. It's got to be more flat. Again, I'm not really here to hammer that, but I am here to say we have 2 groups of kids here. 3. This is their last math class, woohoo. I'm going to pre-calc, and I need to get more foundational stuff, or I'm going to honors. If you're going to honors, you want to be able to say, I know what this graph looks like.
Why would you do negative 2 instead of just 2?
Because this graph is going down, the y's are negative.
Yeah.
Right on this one. And 2, it's going to be like right here. It's going to be pretty small. And I already have that. And so you can see this one, we're going to do one just like it in a moment. This one has a translation vector. So we did it this morning, left 2, up 4. Here's my translation vector right here. Automatically vertical asymptote. We have no stretching going on. So x equals -2 vertical asymptote. And then we go directly to right 1 up 0, right 5 up 1, and right 1/5 down 1. Those are my 3 points. They don't, in tonight's homework, there are no stretches, only translation.
Where would the versus stretch factor go if it wasn't?
You tell me where it would go. It goes in the same place it's always going.
It would just go right before the log file.
Right.
Before the log base file.
That's what A is. A vertical stretch factor goes in front of the function.
I'm getting confused on the right one.
Hmm?
Because you say 1 over b.
I do not say right 1.
I mean right, and then it's like a 1 over the b.
Okay, right 1 over b. What's b in this function?
5.
So what would you say? Right?
Up 0.2.
Right
1.
over, what's b?
5.
So you're going to say right 1/5, or 1 over 5, and then what?
And then down 1.
Down 1. Right 1/5, down 1.
Okay.
Still not seeing it?
Okay.
1 over 5 is a number, right?
Yeah.
It's 0.2 as a decimal. From my translated origin, I went right 0.2 or 1/5, down 1.
Okay.
It doesn't say go right 1 over 5. Over is not a direction. It's right 1 over 5.
Yeah.
Okay, I'm not sure what the confusion is.
Okay, I didn't get. I was just messing up. Now I get it.
What if it was log base 7 of x? What would you do?
Go 0.14.
Okay, let's say I didn't want you to do 0.14, I wanted a fraction.
1 over 7.
Right, 1 over 7,
Up, or then down 1.
down 1. Where's 1 over 7?
It's like, oh,
Don't care, it's teeny, right?
yeah.
So we go right, teeny,
Okay.
down 1.
Okay.
Right 1, up 0. And this one over here, base 5, right 5, up 1. And this one would be right 7, up 1.
Wait, so we're doing the opposite of what we learned in the others.
We're doing, logs are inverses. This is not a b to the x, this is a log. You might have seen this earlier today. Okay, we went through and we talked about yesterday's, or a couple days ago, we did the exponentials. Today we did the inverse of them.
Okay.
And everything switched. So they became, the log is the inverse of the exponential. Domain and ranges all switched. And our critical movements from 2 days ago, which was left 1, up 1 over b, becomes right 1 over b, down 1. We went right 0, up 1, switches to right 1, up 0. We went right 1, up b, we switch them, right b, up 1.
Okay.
So when we're looking at logs, that's how we do our graph. And the more you keep asking the questions when it's not clear. The biggest frustration is that I have people in here not taking notes, I have people who are not asking the questions when they come to them. Ask the questions. Those of you not taking notes, after break, you're going to come back and you are going to be in serious trouble. I'm just telling you what's going to happen. Try this one on your own. See if you can get this one sketched out. So let's start with the list. Parent graph. I think Paige already said it. The parent graph, y equals log base 2 of x. Make sure that 2 is in the base spot. Now let's say you forget your critical movements later, the right, left, you can't remember what to do. Remember, we can use the definition of a log and just make y be -1, 0, and 1. When y is 0, for example, what's 2 to the power of 0?
2.
What's 2 to the power of 0? 1. So that means x is 1, y is 0. You would go right 1 up 0. When y is 1, 2 to the power of 1 is 2. So you'd go right 2 up 1. And when y is -1, 2 to the -1 power? 1 over 2. So you'd go right 1 over 2, down 1. Translation vector for this one? 1, 2. And no stretching, so the vertical asymptote is automatically x equals 1. It's whatever c is. Okay? Can I finish this one?
Yeah, sorry.
So we have a translation vector 1, 2. So right 1 up 2, that's where I'm going to start. The first thing I should put is my vertical asymptote. There we go. From our translated origin, 1, 2, we're going to draw our graph. First point, right 1/2, down 1. Right 1, up 0, right 2, up 1. So we come off the wall, and we look like that. If you want to put some more points in there, that's fine. I only need the 3. I only need the 3. Paige, hang on to your other question. We'll come back to it. Everybody okay with this? What's the domain? X is greater than 1. What's the range? Reals. The x's go this way. They start at the asymptote, push to the right. Greater than 1. Range is always all reals. Okay? 10 to the x and common log of x are always inverse functions. And that's true with all base in log same base. They're all inverse functions. Right? That's the whole point of today. Let's try one more. See how you do with this one? And then we'll move on. All right, let's take a look at the list. We already got the parent graph. Y equals log base 5 of x. Rachel, what's the translation vector for this one? 4, 1. Caitlin, what's the vertical asymptote? X, bless you, x equals 4. So the first thing we want to do is go to 4, 1. And we want to put our vertical asymptote right through that translated origin. Ellie, give me one of the points. Right, 1 over 5. Down 1. Right 1/5, down 1. And again, 1/5, 1/6, 1, it's little. Just get close to the asymptote. Don't get all fired up over having the exact location of 1/5 on this. Just get me close. Nina, give me another point.
Right 5.
Right 5, up 1. Right 5, up 1. Natalie, give me another one. Right 1, up 0. That's my favorite. Then we just climb the wall, roll over the top. Just like that. What's the domain?
Greater than 4, or greater than 4.
How much, Sarah? Greater than 4. What's the range?
All real.
All reals. We love that. Now, we did 11 yesterday. You're going to do 12 tonight. And again, there's no stretching, but it's on graph paper, lots of graphs. If you want to not suffer so much tomorrow, and when we get back, write out, put it on a piece of paper, all the properties of exponents with their names. So product property for powers, quotient property, power of a product, power of a quotient, all of those properties, if you could list them out, it's going to help you tomorrow. What's a log? A log is an exponent. If a log is an exponent, then the properties of logs are going to be exactly the same as the properties of exponents. So if you understand these properties, you're going to do great with the properties of logs. Some of you, I already know, have no idea what I'm talking about with these properties. We've erased it from the hard drive. You need to go back and visit these because that's what we're doing tomorrow.